Hello, this is Jennifer Martinez, and in this video we're going to work on the properties of determinants. And we're going to start with Theorem 3, the properties of row operation. So if A is a square matrix, it says, if a multiple of one row of A is added to another row to produce a matrix B, then the determinant of B is the same as the determinant of A. So we can row reduce, at least do that one operation in row reduction and get a bunch of zeros and not have it affect the determinant. You do have to be careful though, because if you interchange two rows, there is a difference. They are not the same. The determinant of B is equal to negative of the determinant of A. And then if one row is multiplied by K to produce B, then the determinant of B is K times that determinant of A. So two of our row reduction rules do affect the determinant, but we know what they are, and the first one, part A, does not. The proof of this is in the book at the end of the section, if you want to look at it. What I'm going to do is just show why with it that it's so with a 2 by 2. So I'm going to prove it for a 2 by 2. So let's just say y instead of the proof. So let's let A equal a general 2 by 2 A, B, C, D. We know that the determinant of A is AD minus BC. So now I'm going to take K times row 1 and add it to row 2 and put it into row 2. So if a multiple of one row is added to another to produce another matrix, the determinant should be the same. So let's see if they are. So what I'm going to do is I'm going to put K here, and I'm going to say this is reducing this, or row equivalent, to, I'll leave the first row alone, but this would be KA plus C. Might need more space there. And KB plus D. Put the B there to make it look a little nicer. And now let's look at, so we'll call that now B. And let's look at the determinant of B to see if it's the same. So you get, it's a 2 by 2, so it's A times KB plus D minus B times KA plus C. So what happens here is, when you expand this out, and the first terms cancel, so you end up with AD minus BC, which, by the way, was the determinant of A. So that shows that the determinant of B is equal to the determinant of A if you multiply by a row, one row by a constant, and add it to the other. So that is part A. So now let's look at part B. Again, I'm only going to prove this for a 2 by 2. So if I start with my A, and I interchange two rows. So if I make this CDAB, so I'm going to say what I'm doing is I'm taking row 1 and I'm interchanging with row 2. Is the determinant the same? So now we're going to call this B. Maybe I should move that over to the right. So if I look at the determinant of B, that's going to be CB minus AD, which is the negative of the determinant of A. So that proves the second one for 2 by 2. Last one, part C. What if I just multiply or divide through by a constant? So let's take K row 1 and just put it into row 1. What happens there? So for example, I'll do it to the first row, and again I'll call this B, And the determinant of b is what? Maybe I need a little more room. The determinant of b now is going to be KAD minus KBC. So you can see that it does affect the value of this, but at least we know what it is. So again, if I make that a little smaller, you can see part C here, that the determinant of B is K times the determinant of A. So we know it works for this one case for a 2x2. Again, if you want to see the proof, it's at the end of the section. You need a couple of more theorems before you can prove it, but it is there if you wanted to check it out. They do it by induction. It's quite more complicated with a n by n. You can prove it easily for a 3x3 or a 2x2, but for the general n by n case, you'd have to look at the book if you're interested in that. So now let's look at example. Example 1 wants us to compute the determinant of A. So I'm going to do it this new way. So what is the determinant of A? So I know if I multiply by one row and add it to another, it doesn't change the determinant. So I'm going to go ahead and row reduce this to get zeros below that 1. So what I'm first going to do is take row 1, multiply it by 2, and add it to row 2 to get 0, 0, and look, the last one looks like 4 plus negative 9 is negative 5. Then I'm going to do the same thing, but with a 1. Take 1 times row 1, add it to row 3, put it into row 3, get 0. This one you get negative 4 plus 7 is 3, and 2 plus 0 is 2. You can actually stop here. You know these two determinants are the same, so you could go ahead and now do the cofactor expansion. But what I'm going to do is just continue to show you this new method. I'm going to interchange row 2 and 3. I'm going to write it right here because that one, it does change it. So when you interchange rows 2 and 3, you have to add a negative 1. Stated by the theorem. And I'm going to stop here. I'm not going to get this in echelon form. We have our pivots. So we know by the theorem that we did, the last theorem that we did in the last section, the last video, we have a triangular matrix. We can have that negative 1. And we know the answer is going to be 1 times 3. We just multiply by all the diagonals. So the answer should be 15. Again, you could do this right here. Right? The determinant of this one, you can see is negative 5, right? Plus, minus, plus, minus. Oh, so it's actually a 5, and then times 3. It also works because that would be a 0. So, but that is kind of a nice idea to get all those zeros there. It's really nice for larger determinants. It really saves, because this is a recursive formula, if I had to do example 2, for instance, the cofactor expansion, what we would have to do is take this times the resulting determinant, the first row, if you just take the first row, or even the third row, right? Each one times another 3x3 determinant. And if you're doing something like a 5x5 or a 6x6, that can get really long. So let's just look at their solution instead of doing this one, just so you can see it. But they row reduced it. They got a 1 with zeros. I guess they divided through by 2, so they had to add that extra 2 there. But other than that, they kept on going until they got that triangular, and they just multiplied them. The reason I bring this up is because there's a great warning here. Oh, before I get to the great warning, in general, let's do the general first. Let me make that a little larger. So the method that they're doing here is written below. So let's read this. Suppose the square matrix A has been reduced to echelon form, right, by all the different, all the necessary row interchanges and row reductions. It turns out, and say this is U, this is the determinant U. Since U is in echelon form, it's therefore in triangular, is triangular, and so the determinant U is just the products of all the entries. So the determinant A is equal to -1 times the raised to the R times, because of all the interchanges. And again, we're not going to do any multiplication or division, just how many interchanges that we do. So it's going to be the product of all the pivots times how many different changes that we do. This is a great way to, if you're programming, how to find the determinant. This is a great method to use. By the way, if you end up with a row of zeros, right, the whole determinant is going to be 0. So that's why I have the second line here. It's 0 when it's not invertible, when the determinant is 0. Okay, so I have this great numeric note here, what I would like to talk about, because I just found this quite interesting. It says, by today's standards, a 25 by 25 matrix is small. Yet, think about it. If we had to do determinant of that, you would have to expand a row, and then each determinant, right, it's a recursion formula, so each cofactor expansion that you would make would have to be done with a 24 by 24 and so forth. So in general, a cofactor expansion requires more than n factorial multiplications. 25 factorial is a huge number. If a computer performs 1 trillion multiplications per second, it would have to run for more than 500,000 years to compute it. So fortunately, there is better methods that we will soon discover. So I got this from the last section. This is the numerical note in this section. Most computer programs that compute determinant of A for a more general matrix A use the method described in 1, which is above here. It can be shown that evaluations of an n by n matrix using row operation is about 2n cubed divided by 3. So in a modern microcomputer can calculate a 25 by 25 in only about 10,000 operations, much smaller than the method for larger determinants than the last section. So that was just a note for you computer programmers out there. But just so you know, I usually don't really, when I go ahead and solve these, I usually do a combination of the cofactor expansion and the row reduction. So for instance, I might add these zeros up. So let me find the determinant of A, for example, 4. So without even getting to one here, interchanging rows, because I personally don't like to change the value as little as I can. I'm just going to go ahead and add them. I'm going to do a combination of everything that I know. So let's go ahead and do that. So I'm going to take 1 times row 2 and add it to row 4, and then just put it into row 4. So the only thing I'm going to change is row 4. So that would be a 0. That looks like -7 plus 4 is -3, and 3 plus -2 is 1. Then I'm going to use the cofactor expansion. So I realize that that is plus minus, that's in a minus position. And then I'm going to delete the first column and that second row to end up with that matrix. So now what I'm going to do is take -2 times the resulting matrix, and I might go back to row reduction. So I'm going to multiply the first row by -3 and add it to the second to get this row. And that doesn't change the value of my matrix. And then I'm just going to go back to cofactor expansion using that 1. and get the answer.